All right, welcome back to another exciting series of calculus. I'm glad you survived the first series, and you might even be interested to learn more about integration and differentiation. So we just take the ball where we left it off in the previous course with integration, and we add another tool to our toolbox, which is integration by parts. Here, I'm giving you 3 examples, which all look very similar. The integral of sine x dx, the integral of x sine x square, and the integral of x sine of x. And as I will show you in this video, each of these integrals has its own method of integration. So for example here, the first integral you integrate directly. For the second integral we're going to use substitution, yoo-hoo! And finally the last one will not actually be solved by substitution. For the last one we need integration by parts. For example here, integral sine x dx, we can very simply integrate this as minus cosine of x, and then, as you remember, for an antiderivative you have a constant, plus a constant. The second one, integral x sine x squared dx, we use substitution. So we substitute u to be x squared, then we have du to be 2x dx, making du over 2 to be x dx, which is exactly the term in the integral. And so, using substitution, I can write this to be integral of 1/2 sine of u du. Right? So the du half replaces x dx, and the sine u replaces sine x squared. So I can integrate the sine, and I get minus cosine. So it's minus 1/2 cosine of u plus a constant, and then I replace the u, I get minus 1/2 cosine of x squared plus c. Okay, so substitution will solve this equation here. And now on to the integration by parts example. Okay, so here we could try substitution. Well, let's try this, just to show you it does not work. Okay, so a substitution could be u is equal to x, right? Then we have du becomes dx, and we sub the integral, and so then the integral becomes integral of u sine u du. Oops, right? So this is exactly the same integral as before. The idea of integration by parts is to undo the product rule. We have seen substitution undoes the chain rule, so integration by parts undoes the product rule. How can we see this? Well, one idea to see this in this example is you only take one of the two functions and do the antiderivative for only one of them. Okay, so here we have two functions. We have x and we have sine x, and I'm going to do the antiderivative of sine x first. So the antiderivative of sine is minus cos, okay? So we get x minus cos of x. And let me just take care of the minus sign, so minus x cosine of x. And now I do the derivative of this, because of course this will require the product rule, and everything is based on the product rule as I just indicated. So I look at d by dx of this term, minus x cos x. And I just want to see what happens. So what happens is I need to differentiate first the minus x term, which gives a minus, and the cosine is kept, minus cos, and then I keep the minus x term and I differentiate cosine, which is minus sine. Okay, so then I can continue. This is then minus cos x plus x sine x. Perfect. Because now this is the term I'm looking for, right? All of a sudden the x sine x appears, which is what I had here in the integral in the first place anyways. So let's solve it for this. So then we get x sine x equals, I need to move the cosine to the other side, so then this is d by dx of minus x cos x plus cosine of x. And this is something I can now take and put into the integral. Aha, let's try that. So then we have integral x of sine of x dx is equal to the integral of all the right-hand side. So integral d by dx of minus x cos x plus the cosine itself, all dx. Is this easier? I think it is easier. The first term is a derivative, and the indefinite integral of a derivative is a function itself. That's the fundamental theorem of calculus. So the integral undoes the differentiation. So the first bit is just minus x cos of x. For the cosine we integrate and we get sine. And then I add the constant, so then we get this. Who wants a general formula for integration by parts? Who wants a general formula? Of course, everybody. So, to get the general formula for integration by parts, we start again with the product rule. Here it's written, d by dx of f times g is f times g prime plus f prime times g. Okay, we all know this. Now, to get our general form for the integration by parts, we just integrate that thing there. So I write integral of d by dx f of x g of x dx equals the integral of f of x g prime of x dx plus the integral of f prime of x g of x dx. And now on the left hand side again we have the antiderivative of a derivative. Okay, the integral undoes the derivative, and here on the left hand side we get f of x times g of x equals integral f of x g prime of x dx plus integral f prime of x g of x dx. Again, I do not need to write down the constant plus c on the left. I could. I don't need to, because I still have integration to do on the right, and there will be constants to take care of that. Good. And now I solve this for one of the integrals. So I rearrange and I get integral f of x g prime of x dx equals f of x times g of x minus the integral where you flip the derivative. So f prime of x g of x dx. And that's it. So this is the general formula for integration by parts. Okay, so if you look at it a bit, what you have is you have a function f and you have a derivative g prime. And then the first term on the right hand side is both functions without any derivative, f times g. And then the other term is a minus integral where you flip the derivative. So now f gets the derivative and g does not. And the idea of this whole thing is that the function g is something you can actually integrate easily, whereas the function f is something which you can differentiate easily. Okay, let's remove the arrows, because there's another version how you can memorize this formula, and this uses differentials. So let's do that. And many people, including myself, find the use of differentials actually easier in this context. Okay, let's do that. So let's call u to be the function f of x and v to be the other function g of x. And then the du, the differential du, would then be f prime of x dx. Okay, we differentiate by x. And similar for v, so then dv would be g prime of x dx. And now we can write the formula above in the box in terms of u and dv and v and du and so on. See, so the first term, the integral, just becomes u, and then this g prime times dx is from over here dv. So it's just u dv. And then this equals u times v minus integral. And now the f prime dx is du, and the g function is v. v du. Okay, so if you identify the terms in the upper formula, you get exactly this. And this is the formula for integration by parts in differential form. You choose u and dv so that the integrals on the right-hand side are simpler than those on the left. And often you choose dv to be a function and a differential that you can integrate in your head very easily. So let's go back to the initial example, x sine x. Up on top is the integration by parts rule again, and I just write my integral underneath. Okay, written in this form, it is kind of intuitive to call all this to be dv. Okay, and then the u is the original x. So let's write this down on the side. U is an x, dv is sine x dx. So to find the function v, we need to integrate the sine function, which is minus cos. So then I have the u, the dv, I have u and v. I'm missing du. Okay, so then let's do the du. That's the derivative of the right-hand side, so it would just be dx. And then I can sub everything in. So then this is u times v. U is x. V is minus cos x. Minus the integral of v minus cos x times du, and du is dx. Now the question is this simpler than the previous one? Well, I would say it is, because the first one is minus x cos x. The other one we get a plus sign, and then we have to integrate cosine, which of course is sine. And now, as this was the last indefinite integral in all this formula stuff, now I add my constant c. So now I have no more excuses not to use it. So I add the constant c. And that's the same formula as above. Now, with the integration by parts rule, you actually have choices. You can also make a different choice from the original integral, and this might actually not work, as I show you now. So I write down the same integral again, but I flip the order of the terms. Okay, I write sine x and then x dx, suggesting that x dx should be the dv and the u should be the sine. Let's try that out. U is sine x. I know I need du, so that would be the derivative cosine of x dx. Then I have the differential dv to be equal to x dx. So then I need to find the antiderivative of this. So then v would be x squared over 2. Good, we are ready to plug everything in. So then by integration by parts, we get u times v sine x times x squared over 2 minus integral of v. V is x squared over 2. And then du. Du is cosine of x dx. And now it turns out that the integral which we keep here on the right is actually more complicated than before. Okay, so if you have a different choice for the u's and v's and dv's, it might actually not work. This of course means you might have to do it multiple times before you get a really good answer. Alright, let me summarize. So we have seen integration by parts undoes the product rule. The easiest way to remember, I think, is the differential version. Integral u dv equals uv minus integral v du. And then we choose dv to be simple enough so that we can integrate it in our head. And as I say, it might actually not work on the first try. That's how life is. What is this? Ah, maybe Tolo is joining us again. Let's see what Tolo is up to. Hi Tolo, good to see you. What are you doing?